Sure.
All right. So before we start, I want to remind everyone of the community statement for the seminar, which has 3 principles. 1, we are all learning. 2, everyone has something to contribute. And 3, no one has all the answers. Okay, so with that, I'm very happy to have Lorenzo Vecchi, who will be talking to us about Hilbert series of Matroids.
Thank you very much, Sarah. Thanks for the invitation and thanks for the honor of opening this season of seminars. All right, I guess I'll just get right into it. So this is not the first time I give this talk, and whenever people, combinatorialists, look at the title, Hilbert series of Matroids, they come to me a bit scared, asking me, wait, will this be an algebraic geometry talk? Because I don't know anything about algebraic geometry. And to that, I'd like to reply that no, this will not be an algebraic geometry talk. I'm a combinatorialist by background. It's true that I will be talking about some polynomials that come from algebraic geometry, but I will not be using algebraic geometry, heavy algebraic geometry machinery. So you will be fine. And if you know anyone who was scared about the title, please call them back and he can join. So what is my plan? I want to talk to you about matroids. I look at the past abstracts and I didn't see matroids in the title of the last talks. So I will very gently introduce you to this beautiful theory, and I will show you some nice invariants that have some geometric interpretations. I will show you that there were some conjectures that were open and people were able to solve them using geometric machinery, even if the conjectures were purely combinatorial. And as a way for combinatorics to win back this fight with geometry, I will also show how combinatorics makes life easier when you try to compute some geometric invariants. And I will show how we were able to give some partial answers to combinatorial and geometric conjectures with just combinatorial tools. And everything I'm talking about today comes from a joint work with Luis Perroni, which is now at KTH, Jacob Modern from University of Bonn and the Max Planck Institute, and Matthew Stevens, also from the University of Bonn. All right, so let's start by asking ourselves, what is a matroid? Oh, and please feel free to interrupt me at any time. I will try to look at the chat, but if I don't reply, just barge in and ask the question with the microphone. Okay, so what is a matroid? Let's start with something that everyone should be familiar with, which is linear algebra. So let's take a matrix with entries in some fixed field K. And these are three nice properties about the columns of any matrix. The first one is that if I take no columns, so the empty set, this is linearly independent. So I don't have any linear relations between 0 vectors. Then if I have an independent set of columns and I take a subset, this is still independent. So I cannot create new relations by deleting vectors from my family. And then if I start with an independent set, I have an algorithm that lets me add additional columns to that set to create a basis of the vector space, which is the space spanned by the columns of my matrix. And I want to claim that these 3 properties tell me everything I need to know about linear independence. Because I have a base case, the empty set, I know how to go down, being independent is downward closed. And then I have a way of constructing bigger independent set from smaller ones. So these 3 properties will be my axioms for what a matroid is. So what is a matroid? A matroid is a combinatorial object that tries to take this notion of linear independence and try to abstract it and generalize it in a combinatorial way. And you can always think about vectors in vector spaces for now. So it is a pair E curly I, where E is a finite set of size n, and I will call it the ground set. And then curly I is a collection of subsets of E, which are called independent sets. And these sets satisfy those 3 properties. So the empty set is independent, every subset of an independent is independent. And then if I have an independent set I, and I know that there exists an independent set J of bigger size, I can always add something to I to make it independent. Okay, so now that I gave you a definition of matroids, matrices or vectors in vector spaces are what is called a k-realizable matroid. So if I can take this combinatorial object and see it as a list of vectors, it's k-realizable. And if I'm able to realize my matroid over any field, I'm going to call it a regular matroid. Dually, I can try to think about it in a different way. Instead of looking at vectors, I can take the orthogonal complement of each vector and consider a hyperplane, and then consider this list of n hyperplanes, which is also called an arrangement of hyperplanes. So in this figure, for example, I had this blue vector v1, and I transformed it into this blue plane in the three-dimensional space. Why is this nice? Because I also want a way to work with geometry. So working with hyperplane arrangements gives me a nice geometric object, which is the complement of the hyperplane arrangement. So I take the union of all the hyperplanes, and then I remove it from the vector space, and I look at what is left geometrically. And so this is a first example of how matroid theory is kind of a bridge between geometry and combinatorics. So the leitmotif, like the fil rouge that for this talk, is that I can always look at things geometrically on hyperplane arrangements, and then I have some nice geometric properties, and then I can try to generalize them to combinatorics by looking at what happens with all matroids. And at this point, you might ask, okay, fine, you are creating this new theory, but was it really necessary to take vectors or hyperplanes and give them a different name, which is matroid? So the answer is yes, because I will show you a different example of matroid. This one comes from graph theory. So I'm going to build a matroid from any multigraph, so I can also allow parallel edges or loops. My ground set will be the set of edges of my graph, and I will say that a subset of the edges is independent if it doesn't contain any cycle, or in other words, if it's a forest. And let's check if this definition satisfies the axioms for matroids. So the empty set of edges is independent because it doesn't contain any cycle. If I take a forest and I remove some edges, it's still independent, it's still a forest, so it satisfies the second axioms. And then we also have a theorem that says that if we start from a forest in any graph, we can keep adding edges to my family such that at the end we get a spanning forest, so a bigger subgraph that also still doesn't contain any cycle. So graphs are also matroids, and we're gonna call matroids that come from graphs graphic matroids. So at least now we have two completely unrelated examples, linear algebra and graph theory, that can be reunited under the same name, which is matroid theory. And if you look really close about these two examples, you're gonna start seeing a lot of similarities. And actually, this is how matroid theory started in the 30s. For example, we have different theorems coming from the two subjects that are actually the same theorem, just with different names. So for example, everyone should recall the fact that if we work in a finite dimensional vector space, we have the notion of dimension, and the dimension is the cardinality of every base. So in a finite dimensional vector space, every basis has the same size. While in graph theory, we have a different theorem that states that spanning trees in a graph always have the same cardinality. And if you look at this now, you're going to realize that this is exactly the same statement about independent sets of two different matroids. One is realizable and the other one is graphic. Okay, so at least now we have a motivation of studying matroids. It kind of unites these two different subjects. But you can still argue that maybe it wasn't that necessary to create a completely new theory. So, because, okay, graphs and vector spaces may not be enough for you. So I always like to include the next theorem in my slides. Actually, this is a theorem by Nelson from 2018, and it states that 0% of matroids come from either of these two classes. So, which means that asymptotically, as the cardinality of my ground set grows to infinity, the chance of picking a matroid at random and it coming from one of these two classes approaches zero, and actually it approaches zero really fast. So matroid theory is a theory with its own dignity, and where hyperplane arrangements and graphs are just a small motivating example, but there's a lot more in the theory to discover. So now that I hope that I have everyone on board and everyone thinks that matroids are really cool, let me give you some more terminology. A maximal independent set is called a basis. This of course comes from linear algebra. A set that is not independent is called dependent, and a minimally dependent set will be called a circuit. This term comes from graph theory, where circuits in a graphic matroid are exactly the cycle of the graph. And then we also have a notion of the rank, and in realizable matroids, this is exactly the rank function on vectors. So it's the dimension of the subspace spanned by the vector. Here's some examples now. The uniform matroid is a matroid that depends on two parameters, k and n. N is the size of the ground set, and k is the rank of the matroid. And this matroid can be realized as a list of n vectors in a k-dimensional space in the most general position possible, meaning that every k subset of my ground set needs to be a basis. So for example, the uniform matroid U23 can be realized by three vectors on a plane, such that every pair of vector will span the entire plane. So in this figure, you have one possible realization of this matroid. If we take k equal to n, this will be called the Boolean matroid. So for example, if we want to look at the Boolean matroid B3, we are looking at three vectors in a three-dimensional vector space, such that all three form a basis. So any basis of any vector space will be a Boolean matroid. One last definition that I would like to give on matroids is the concept of flat. A flat is a subset of the ground set E that is closed under rank, which means that every time I try to add an element to my subset, the rank increases. And if I take all the flats of my matroid and I order them by inclusion, remarkably, this forms a lattice in the poset theory sense. And we call this the lattice of flats of the matroid. So for example, if I take the example that I drew before, so these five vectors in a three-dimensional vector space, the nice thing about it is that if the matroid is realizable, flats are in bijection with the subspaces spanned by my list of vectors. And the rank is exactly the dimension of the subspace. So if I take the empty set, and the empty set of vectors, this spans the origin, which is the only zero-dimensional subspace. If I take any of the vectors independently, they span 5 different lines. These are the 5 one-dimensional subspaces, or the 5 rank 1 flats. Now in dimension 2, something interesting happens. If I take V1 and V2, they span this orange plane. But if I add V3 to it, they still span the same plane. So 1, 2 is not a flat, because if I add 3, the rank does not increase. But 1, 2, 3 is a flat, because then if I add 4 or 5, I span the entire space. So 1, 2 is not a flat, but 1, 2, 3 is, and that's why I draw it here in the rank 2 flats. And the same thing goes for 3, 4, 5. While all the other pairs, like 1, 4, 1, 5, 2, 4, and 2, 5, they all span a different plane. And these will be all the planes that I can span in my matroid. And then of course, if I take all the possible vectors, they span the whole vector space. So the ground set is always a flat of my matroid. We talked about uniform matroids. So what is the lattice of flats of a uniform matroid? For example, if I take the uniform matroid over 4 elements of rank 3, how does the lattice of flats look like? I still have the empty set. I have the 4 lines spanned by 4 vectors. And now, since I asked the vectors to be in the most general position possible, this exactly means that every pair of vectors spans a different plane. So all the two subsets of my set of 4 elements will be flats. and then I reach the whole ground set again. So in the uniform matroids, flats are subset of size less than the rank, and the whole ground set again. Why am I so interested in this kind of lattice? Well, there is a theorem that states that there is a correspondence between matroids and geometric lattices, with geometric lattice meaning that it's a lattice that is both atomistic and unimodular. And the correspondence goes like this. If I have a matroid, I can always build the lattice of flats, and this lattice of flats will be a geometric lattice. But the other way around is more interesting. So whenever I start with a geometric lattice, I can always build a matroid such that its lattice of flats is isomorphic to the starting geometric lattice. So now the claim is that I can talk about matroid by talking about lattices. So I'm moving from the hyperplane arrangement idea and going to a more combinatorial world where I'm working with posets. What is a nice thing that we can do on any poset? We can compute the characteristic function chi, and we can do it by computing the Möbius function of the poset. If someone has never heard of it, let me just try to do it with a quick example. So it works like this. I start from a minimal element and I give it the value 1. Then I look at any other element. I look at everything that is below it. I sum all the values that I already gave recursively, and then I change the sign, and this is the value I'm going to give to that element. So for example, under 1, we only have the empty set, which has value 1. So I change the sign to a -1. So all the atoms of this poset will get the value -1. Now, for example, for 1, 2, 3, what is below it is 1, 2, 3, and the empty set. So I sum all those values. This gives me -3 plus 1, it's a -2. I change the sign, so I give to that element the value +2. And the same goes for 3, 4, 5, that has these 3 elements and the empty set below it. While, for example, 1, 4 only has 1 and 4 and the empty set below it. So this will be -1, -1, +1, which is a -1, and I change to +1. And then lastly, I take the sum of all these values. This is 2, 3, 4, 5, 6, 8. -5 is 3, +1 is 4. And that's why the whole ground set gets value -4. And this is how you compute the Möbius function. So what you can do now is you can add over the elements in the same row, which are the flats with the same rank, and reading them bottom upwards, you get the coefficients of a polynomial. So you have 1, -5, 8, -4, and this becomes the coefficients of this polynomial. And we call this polynomial characteristic polynomial of M. Why is this polynomial interesting? Because it records a lot of information about our matroid. So for example, if the matroid is graphic, what is a nice polynomial invariant for graphs? It's the chromatic polynomial. And remarkably, you can compute the chromatic polynomial of your graph just by taking the characteristic polynomial of your matroid and then multiplying it by x to the number of connected components of your graph. So that's great. We are generalizing the chromatic polynomial to add to all the 100% of matroids that are not graphs. Moreover, if we have a matroid which was realizable, so we have a hyperplane arrangement, we might want to have some geometric information about the complement of the arrangement. And it's incredible how the characteristic polynomial gives us information for any field we are working on. So if we are working on a finite field, our vector space is a set of discrete points, and the complement of the arrangement is a set of discrete points. So we might want to compute how many points are there in the complement. And this is given by the characteristic polynomial, which gives us exactly the cardinality of the complement. Now, if the arrangement is realized over real numbers, every hyperplane cuts the space in half. So we might want to know how many connected components are there in the complement. And this is again given by the characteristic polynomial. Lastly, we can also realize our arrangement over the complex field. So we have a theorem that says that we get a variety that is smooth, and we might want to compute its cohomology, and the Hilbert series of the cohomology of the complement is again given by the characteristic polynomial. So this polynomial is a great invariant because it gives us both combinatorial and geometric information about any matroid we're working with. So just as a quick recap, we said that we were on a bridge between geometry and combinatorics. On one side, we have hyperplane arrangements that can be generalized to matroids. These hyperplanes can intersect in some nice way, and we can record it with an intersection poset. And these exactly correspond to the lattice of flats of our matroid. On the lattice of flats, we can compute the characteristic polynomial, which is a combinatorial object. But this polynomial also gives us a geometric information. It's the Hilbert series of the cohomology of the complement of the hyperplane arrangement. But if we're not interested in geometry, this is great news for us, because if we're interested in geometry, we were able to compute the Hilbert series of the complement of the arrangement without actually having to build the cohomology ring, which is always the daunting part of computing cohomology. We just did it combinatorially on the lattice of flats. But now, if we are not interested in geometry, we now have an invariant for every matroid, not just the 0% that is representable, because it's just computed on the lattice of flats. And moreover, this invariant is not just there, it still gives us combinatorial information, even when we are not thinking about hyperplane arrangements. So we have an invariance that encodes combinatorial features of the matroid. For example, the chromatic polynomial of a graph. So this is a first way of combinatorics helping geometry and getting something in return. We helped geometers computing cohomology, and now we get a nice invariance. But the helping hands goes the other way around as well. We had two big conjectures in matroid theory that have been open for decades. And these are purely combinatorial conjectures. Let's have a look at them. The first one is the Heron-Rata-Welch conjecture. It states that for every matroid, the characteristic polynomial has log-concave coefficients, meaning that all the coefficients of the polynomial satisfy this inequality. And the second conjecture is the top-heavy conjecture. It's a conjecture on the number of flats inside the lattice of flats. And it says that the number of flats in some rank satisfies this inequality. And as you can see, these conjectures are combinatorial. They can be formulated in a world where geometry does not exist, but they were only solved after like 50 or 60 years in the last 10 years. And the only proof that we have for now is a proof that comes from geometry. So it's a proof that is inspired by the geometry of hyperplane arrangement that takes some properties of realizable matroids and then moves it to the combinatorial world. So let me give you a quick recap of how these conjectures were proven, unless there are any questions on general matroid theory. So the first geometric objects that I have to talk about is the Chow ring of a matroid. Chow rings, if you're not algebraic geometers, Chow rings is just a fancy name for cohomology. So you can think of cohomology, but it's a bit different. So that's why we need to use this separate term. So we said that we needed to start from geometry. So we have to start from hyperplane arrangements. And there is a nice variety associated to hyperplane arrangements, which is called the De Concini-Procesi wonderful model. So you take the arrangement, you put it into a projective space, and then you do some explicit algorithm to create some variety. And then you want to compute the cohomology of that variety. So the geometric objects that we're interested in now is the Chow ring of the De Concini-Procesi wonderful model of some arrangement. So of some realizable matroid. This is a geometric object, but we also want a definition of this ring for all the other matroids that are not realizable. And thanks to Feichtner and Judzwinski, we have a way to realize a Chow ring for any matroid. as a quotient of a certain polynomial ring. So we have these polynomials with coefficients in Q, and we have a variable for every flat that is not empty or the whole ground set. And then we take this polynomial ring and we quotient out by two ideal subrelations. And these ideal subrelations mimic exactly what should happen inside the Concini-Procesi wonderful model. And so Falkner and Jusvinsky were careful with defining this Chow ring in a way so that if M was actually realized by an arrangement, this combinatorial version of the Chow ring is isomorphic, of course, to the Chow ring of the wonderful model. If we're not interested in geometry, one thing we can look at is the Hilbert series of this Chow ring. We denote it with underlined H, and we call it the Chow polynomial. We have two theorems coming from independently from Adiprasito, Ha, and Katz from 2018, and Braden, Ha, Mathern, Proudfoot, and Wang from 2022. And this theorem says that this Chow ring satisfies Poincaré duality and the Hard-Lefschetz theorem. Again, these are geometric properties, but I can give you a nice explanation combinatorially. Poincaré duality implies that the Hilbert series is a palindromic polynomial, so it's symmetric with respect to the middle degree. And the Hard-Lefschetz theorem says that the Hilbert series of the Chow ring is unimodal, meaning that the coefficients go up until a certain point, and from that point on, the coefficients go down. In this setting, so with this machinery, starting from realizable matroid and then moving from a combinatorial version of this Chow ring, this is how Adiprasito, Ha, and Katz proved that the characteristic polynomial is log concave by relating the coefficients of the polynomial with some one forms inside this cohomology ring. There is also a different variety called augmented Chow ring. We still start from the hyperplane arrangement in the realizable case, build a variety, which is called augmented wonderful model, and then look at the cohomology. And again, we can also define a combinatorial version of this augmented Chow ring for non-realizable matroids. And we can still look at the Hilbert series of this augmented Chow ring. And there's a theorem by Braden, Ha, Mathern, Proudfoot, and Wang that states that also the augmented Chow ring satisfies the Poincaré duality and the Hard-Lefschetz theorem, meaning that the Hilbert series is also a palindromic unimodal polynomial. What do we know in general about the Hilbert series of these objects? Not much. We know what the Hilbert series are for Boolean matroids, again, from these two different separate sets of authors. For the Chow polynomial of the Boolean matroid, the answer is the Chow polynomial is the nth Eulerian polynomial, the one that you compute the descents of the symmetric group, which is, I don't know, very weird to me that happened. But it's exactly that polynomial. And then for the augmented Chow polynomial, the answer is something called the binomial Eulerian polynomial, which is just a sum of Eulerian polynomials that are weighted by some binomial coefficients. So this is a nice answer, a nice combinatorial answer. Regarding the uniform matroid, we have a theorem from Heimeister, Rao, and Simpson from 2 years ago that gives us the coefficients for the Chow polynomial in terms of some combinatorial statistics. These formulas are not nice enough to actually compute the polynomial for big matroids, so it's not the best we can achieve. And moreover, they give no information on the augmented Chow polynomial. And so in a sense, in matroid theory, can someone remind me what the difference is between the H and underlined H? Yes. So underlined H, which is this one, is the Chow polynomial, which is the Hilbert series of the Chow ring. H without the underlined is the augmented Chow polynomial, which is the Hilbert series of the augmented Chow ring. I know that this is the standard notation. I don't particularly like it because it's just an underline, but this is how they are called in literature. So
thank you so much.
Thanks for the question. And yeah, so Boolean matroids and uniform matroids are kind of the level one in matroid theory. If you want to prove something for all matroids, you start from here. And the fact that even for uniform matroids, we don't have nice answer, meant that there was still a lot of work to do. One nice thing about these two polynomials is that they're both conjectures to be real-rooted. For the Chow polynomial, it's due to Ferroni and Schroeter, and for the augmented Chow polynomial is due to Stevens. What is the issue with trying to tackle this conjecture? We have no fast formula to compute them, or like a closed formula or something that we can feed into a computer. And the problem is that the only way of computing these polynomials for general matroids is building the Chow rings and then looking at the dimension and then taking the Hilbert series of those rings, which is something that cannot be achieved for general matroids, even with computers. So what we would like to do is being able to compute these two polynomials on the lattice of flats as we did for the characteristic polynomial without actually needing to build the cohomology rings. And to do that, so this was one of our main goals for the paper. And to do that, oh, does this conjecture come from geometry? Real-rooted sounds like a geometric thing. No, so what happened is that I will try to give some evidence later, but the idea is that they started computing these polynomials, and these polynomials are symmetric and palindromic. So one nice thing to ask for a palindromic polynomial is if it's real-rooted or not. And it just happened that for every example that they computed, they always got a real-rootedness. There might be some nice geometric interpretation, but I'm not aware of that. So maybe, but I don't know. Okay, so we want to compute these polynomials on the lattice of flats. And to do that, I'm gonna go to the second characters of our story that also give us the answer for the second conjecture that I was talking about. And these ones are the Kazhdan-Lustig polynomials and the intersection cohomology module of a matroid. So this is the definition of the two polynomials. They are denoted with P for the Kazhdan-Lustig polynomial and zeta for the zeta polynomial of the matroid. And this polynomial come from the Coxeter theory, and they are a generalization of the Kazhdan-Lustig polynomial for intervals in the Coxeter order. So that's where the name comes from. And they are defined recursively, and the recursion goes like this. We have a base case. So when the rank of the matroid is 0, the Kazhdan-Lustig polynomial is either 0 or 1, depending on the fact that the ground set is empty or not. And then if the rank is greater than 0, you look at all the flats in the lattice of flats, you restrict to them, so you build a smaller matroid and compute its characteristic polynomial. Then you contract the flats, so you build a separate different matroid, which is smaller, and compute the Kazhdan-Lustig polynomial recursively. You multiply them and you sum them all up, and what you obtain is the Kazhdan-Lustig polynomial of the matroid with flipped coefficients. And if you know Coxeter theory, this is exactly what happens when here you have the R polynomial. The zeta polynomial is kind of the same. You take all the flats in the lattice of flats again, you compute the same contractions, so Kazhdan-Lustig polynomial of small matroids, and then you weight the sum with x to the rank of the flats you're quotienting by. And you can also look at these formulas, and if you are keen to poset theory, you might recognize the convolution product from the incidence algebra, and actually these statements can also be given with the convolution product. All right, this formula is not nice to work with. For humans, even small matroids become impossible. It becomes impossible to compute the invariants. Computer handle recursions a bit better, but even then, if the matroids become too big, the formula becomes untractable. However, we have some nice formulas. So for example, here's a formula for the coefficients of the Kazhdan-Lustig polynomial of uniform matroids. But in general, Kazhdan-Lustig polynomials for general matroids are still hard to compute. For example, it's still an open problem to determine what the degree of this polynomial is. for a generic matroid. It's nice though, because if we give a computer enough time, we can produce a lot of polynomials for different matroids. It becomes slow, but you can just leave it there for days and then look at a list of polynomials and you can formulate conjectures. And one of the conjectures is that both the Kajian-Lustig polynomial and the zeta polynomial are real-rooted, which might not be a coincidence when we get to the end of the talk. If you understand what the pattern is with this talk, now we have to look for a geometric interpretation for these polynomials. So we take a realizable matroid, we take the arrangement, we build a different variety, which is called the Hilbert variety. This variety is not as nice as the wonderful model, which was wonderful, because this variety is full of singularities. So we can't use ordinary cohomology, we need a more refined version. And this is called intersection cohomology. And it's just an invariant that also gives us information on where the singularities are on the variety. And the zeta polynomial is the Hilbert series of the intersection cohomology of this Hilbert variety. And then we can take the stock at the empty flat, whatever that means. It's a submodule of the intersection cohomology. And the Kajian-Lustig polynomial is the Hilbert series of that. And now that we have this geometric interpretation, this gives some justification for how ugly that formula was. The reason why we need to define it recursively is because the intersection cohomology of this variety behaves like that. So it's a shadow of a geometric fact on the degrees inside this intersection cohomology. Now that we have this geometric interpretation, we need a version for non-realizable matroids. Braden, Hamad, and Proutut and Wang were able to define the intersection cohomology module IH of M for every matroid. And now the Kajian-Lustig polynomial and the zeta polynomial will be the Hilbert series of these. And this module also satisfies Poincare duality and hard Lefschetz. So the zeta polynomial is a palindromic unimodal polynomial. And they do the same thing with the empty stock at the empty flat and take this submodule, and they say that the Kajian-Lustig polynomial is the Hilbert series of that. So to say that again, this is a corollary. Once you can interpret this polynomial as Hilbert series, you get that the zeta polynomial is non-negative because it's a Hilbert series and it's palindromic and unimodal, while the Kajian-Lustig polynomial is non-negative because it's an Hilbert series. And the weird thing is that this corollary here, the fact that the Kajian-Lustig polynomial is non-negative, actually implies the top-heavy conjecture. So the number of flats inside the lattice of flats satisfy this inequality because this Kajian-Lustig polynomial has non-negative coefficients. And that's because this is a Hilbert series of a module that behaves in a certain way. And that's why the top-heavy conjecture, that's how it was solved, and that's why the proof is only geometric, even if they were able to do it for general matroids in a combinatorial way. So what do we have now? We have, on one hand, we have the Chow polynomial and the augmented Chow polynomial. They are non-negative and unimodal because they are Hilbert series of nice cohomology rings. But the fact that they come from geometry makes the combinatorics very obscure. On the other hand, we have the Kajian-Lustig and zeta polynomial. They were defined combinatorially. This made it easier to formulate conjectures and study combinatorial properties. But the formula was not nice because it was recursive. So when they tried to prove the non-negativity and the unimodality, it couldn't be done combinatorially. They had to do it geometrically. And this was very hard to do for them. And then and I'll say it again, all these polynomials are conjectured to be real-rooted. So there has to be a sort of parallel between these two pairs of polynomials. And here's where we came in, and in the last 15 minutes, I'm gonna give you some new results. The first result in our paper, the main result, is that we were able to give a formula completely combinatorial for the Chow polynomial and the augmented Chow polynomial. It's a recursive formula, so we have some base case, and then we compute the Chow polynomial by looking at all the flats in the lattice of flats, and then computing the restriction and the contraction, and the Chow polynomial of smaller contractions. And then we define the augmented Chow polynomial as a weighted sum of regular Chow polynomials. This is great because now we can stop caring about the cohomology ring. We can just look at the lattice of flats. Again, this was a combinatorial proof, but if you're really interested in geometry, there is a way of taking these formulas, looking at the wonderful model and the augmented wonderful model, and make sense of this new combinatorial formula on the Chow ring of those varieties. So we are not completely losing the geometry. We still have both paths going on at the same time. We missed a formula for the Chow polynomial and augmented Chow polynomial for uniform matroids. And now that we have this combinatorial formula to compute them, we have a clean formula for the uniform matroid. In here, this polynomial dj is the derangement polynomial, again, the one that you compute in the symmetric group that counts the number of derangements. And the augmented Chow polynomial is very similar to this, but we just replace this with the Eulerian polynomial, again, with the Eulerian polynomial. And this is great, first, because these are closed, fast formula to compute these polynomials for uniform matroids. Moreover, the only way to show that these polynomials were non-negative was to interpret them as Hilbert series. But now with these new formulas, these two polynomials are non-negative, and so are these. So the whole polynomials are non-negative. And this is a way of showing non-negativity with just combinatorial means. And we don't need to interpret them as Hilbert series anymore. So if you're paying attention, I told you that recursive definitions are bad. So I got all excited because we had a combinatorial formula, but the formula was recursive. So why are we so happy? Well, the fact that this is recursive, but is a convolution, was used by Ardila and Sanchez in 2022 to prove that the Cauchy-Lustig polynomial and zeta polynomial are valuative invariants. What does it mean? It means that to every matroid, I can associate to a polytope. I can cut those polytopes, I can compute the invariance on the smaller pieces, and then I can compute the invariant of the bigger polytope with inclusion exclusion. And this is what valuative means. And they do it by using the fact that these were defined using convolutions. And now, since these are defined by using convolution products, we were able to show that these are also valuative invariants. So this gives us a way to compute the invariance of big matroids by using the invariants that we know for smaller matroids. And let's see how we used it. There are two classes of matroids that are interesting in matroid theory. They're called sparse paving and paving. You don't need to know the definition for the purposes of this slide. But one nice thing is that they are conjectured to be 100% of the matroids, which again means that asymptotically, as the ground set grows to infinity, the proportion of picking at random a sparse paving matroid approaches 1. And by exploiting the fact that these polynomials were valuative, we were able to prove these formulas for the Cauchy-Lustig polynomial and zeta polynomials. This comes actually from an earlier paper that I wrote with Luis Ferroni and George Nasr from the University of Oregon. And these formulas are nice because they are just in terms of uniform matroids of smaller rank or size. So this is a closed formula for almost every matroid, and it just uses the Cauchy-Lustig polynomials of uniform matroids, which are fast to compute. And now, since the Chow polynomial and augmented Chow polynomial are also valuative, we were able to produce the same formula for these polynomials. So now we know what the polynomials are for uniform matroids, which implies that we know the formula for every sparse paving matroid, which are asymptotically all matroids. How fast did the computation become with these new formulas for sparse paving matroids? Sorry. So in an earlier paper with Luis Ferroni, we computed the Cauchy-Lustig polynomial and zeta polynomial for all sparse paving matroids with at most 30 elements. And this is in the order of the millions of matroids. So this is huge evidence that these polynomials are real-rooted. Now that we have the same formula for these two polynomials, we computed the polynomials for all sparse paving matroids with at most 40 elements, and all the polynomials are real-rooted. So this is huge empirical evidence that the formulas are true. The conjecture is true, sorry. And now you might argue, what if I want evidence for all matroids? I don't like this asymptotic behavior talk. I want something that works for every matroid, not just for a class that is conjectured to be predominant. So when I get a palindromic polynomial, I can rewrite the polynomial in a different basis and use half of the coefficients to get a different polynomial, which is called the gamma polynomial. So I take these coefficients and I build a separate polynomial. If this new polynomial has non-negative coefficients, I say that the original polynomial f is gamma positive. This is interesting because if I work with palindromic polynomial, I have this chain of implications. So real-rootedness is stronger than gamma positivity, which is stronger than unimodality. Now, if you recall, 3 of these 4 polynomials are proved to be unimodals. So we are here and we need to reach real-rootedness. So gamma positivity is a nice stepping stone in trying to prove the conjecture for all matroids. So actually, with Luis and George, we conjectured last year that the zeta polynomial was gamma positive for every matroid. And in this paper, we proved that the zeta polynomial, the Chow polynomial, and the augmented Chow polynomial are gamma positive for every matroid. So not just the sparse paving, but every matroid has gamma positive polynomials. And in my last slides, I'm gonna give in 2 minutes a sketch of the proof, just to highlight what the pattern of this talk is. We used 2 theorems. These are geometric theorems, but we did not care about geometry. We just used them to produce a fact, a combinatorial fact on the polynomials. The first one is due to Braden-Hammer-Plaut and Wang. It's a semi-small decomposition of Chow ring and augmented Chow ring, meaning that these rings can be split in a direct sum in a nice way. And this is a geometric statement. And the second theorem is a theorem by Braden and Visogoretz. It's a deletion formula for zeta. This is a combinatorial formula, so the paper is combinatorial. But even there in the introduction, they say, we gave you this combinatorial formula, but beware that this actually comes from geometry, and this is why this combinatorial statement is true. And using these 2 statements, and just by translating them into to the Hilbert series of those rings and modules, we were able to show that the gamma polynomial of the Chow polynomial, and it's the same for the augmented and the zeta polynomial, could be written as this sum. All these matroids are smaller matroids. So by induction, we can say that all these polynomials have non-negative coefficients. Products and sum of non-negative polynomials are non-negative. And so all this sum has non-negative coefficients. So once we had for free this geometric statement, the fact that all these polynomials were gamma positive was just a very simple induction. And I guess this is the last result that I wanted to talk about. So thank you for your attention.
Great talk. Questions for Lorenzo? Oh, it looks like there's one in the chat.
Okay, let me open the chat. Okay, been proven to be gamma positive. So the Chow polynomial and the augmented Chow polynomial, yes, we did that. So let me go back. So this is our theorem. This is the Chow polynomial and augmented Chow polynomial here. So yes, regarding the Kajian-Lustig polynomial, the Kajian-Lustig polynomial is not palindromic. So this theorem here says that this chain of implications hold if the polynomial is palindromic. The Kajian-Lustig polynomial is not palindromic, so we cannot use this. There is a notion of gamma positivity for non-palindromic polynomials, but the Kajian-Lustig polynomial does not satisfy that. So for the Kajian-Lustig polynomial, the conjecture is still, well, I mean, we have no improvement. So the improvement works for 3 out of 4 polynomials.
Other questions?
Hi. So first of all, this was such a great talk. I've not seen this clear of an explanation of hyperplane arrangements related to vector spaces related to matroids. That was really, really fantastic to see.
Thank you very much.
Well, I have 2 questions. One is, you seem to understand the augmented Chow ring well. I would love to, I think you defined it here and I think I missed it. Would you mind talking about how it's defined again? If it's quick, you know, I don't want to.
Yeah, so
I don't theory.
Maybe I can just open a new slide. I didn't actually show you the combinatorial definition, but basically the idea is that, so you again start with a polynomial ring, but now you will have more variables. You still have one variable x for every flat that is non-empty, I will say, or maybe not the ground set, one of the two. And then you have a variable y for every I in the ground set. And then you quotient out by some relations. Some relations come from the ordinary Chow ring. And then you have other relations. I don't really remember all of them now, but they go something like this: yi minus x of f for all the flats that contain I is equal to 0, or something like that. But I can send you a reference, and like it's one of the first definition in the paper, and it's just this polynomial ring is what we will call the augmented Chow polynomial. So do not quote me on this. There might be some additional relations, but they are this kind of easy. So
yeah,
take these variables, and here's a polynomial which will be 0 in our ring.
Yeah, that's great. I guess it's okay. I don't get the reference. You know, I think I've seen it before. I'm just being lazy and not doing the work of understanding it and asking you to do it. Yeah, thank you. That's very helpful. That makes sense.
Okay, well, while we're in this question, perhaps could you show us the slide where you reviewed what the corresponding definition of the Chow ring is?
You mean for like the combinatorial version of the Chow ring?
Yeah.
Or the geometric interpretation? Which one? Sorry.
Well, do you have 2 definitions defining them as quotients?
No, so the combinatorial definition is one, and it's with just quotients. Let me just go back to the slide so I don't mess this up. Here. Okay, so I said before that we get these variables, one for every non-empty proper flat, and here are the relations. This one here says that you take 2 different elements of the ground set, you take the sum over all the flats that contain the first one, and you take the sum of all the flats that contain the second one, and this will be 0 inside the Chow ring. And then we want to say that if I take 2 flats in the lattice of flats that are incompatible with respect to that order, their product is set to 0. If you need to understand this geometrically, let me try to zoom in. I mean, basically what happens, this might be a too complicated example, but the idea is that you take a generic hyperplane here, for example, this one, and then you look at how it is transformed. We are performing a series of blow up. So we're blowing up all the intersection of these hyperplanes, and we get a figure that looks like this. And then you look at how this hyperplane is transformed inside of here. And basically you're saying that if you take any generic hyperplane, you get something that looks like this as a divisor. And we're saying that if I move this hyperplane around in the projective space, I might get something that looks like this, but since it's the same hyperplane, the corresponding class in the cohomology ring needs to be equal. While the second relation here basically says, I don't know if you can see it clearly, but basically we're saying that the divisors corresponding to flats. So here you have some varieties corresponding to each of the flats. That's why we get a variable for each non-empty proper flat. And when we blow up some things, so I'm blowing up all of these, basically what I'm saying is that if two flats are incompatible, the two divisors will not intersect anymore. And that's why their product is set to be 0. So for example, the blue one here and the yellow one here are incompatible flats. And if you look in here, the blue divisor and the yellow divisor do not intersect anymore because we blowed up their intersection. And that's why their intersection is empty and the product of the variables is set to 0. I don't know if this is a good enough explanation.
Oh, thank you. I think it will be very helpful for somebody like me trying to make sense of it. Thanks.
I think there was maybe one more question in the chat too.
Is there hope to use interlacing polynomial techniques to prove these polynomials are real-rooted? This is a great question. And actually, they try to use this interlacing technique. And there is one small issue. I mentioned it briefly, but I don't know if you caught it. One issue that we need to prove that the roots interlace, like one condition is that you need the degree of f and g to either be equal, or you need the degree to be, like the difference need to be at most 1. And one issue, for example, with the Kajan-Lustig polynomial is that it's an open problem to determine the degree of the polynomial. So this is a bit discomforting because we actually don't know what the degree of these polynomials are. It would be great to know it, but we still don't know what the degree is, so we still don't know whether we can use interlacing techniques or not for the Kajan-Lustig polynomial. So this is a path that people try to explore, but we're stuck at this point at this moment.
Any other questions?
I have one more, but I don't want to take up too much time. It's
No?
I seem to remember that your paper, maybe, I think this most recent one, conjectured things about giving a combinatorial proof of the Chow ring, but I forget what now I'm forgetting it. And I was again being lazy and asking seeing if you could remind me, but maybe I'm misremembering it entirely and I'm thinking of something else.
Oh, okay, maybe I know what you mean. So we have a theorem now due to that set of authors that says that the Kajan-Lustig polynomial is actually a polynomial with non-negative coefficients. And the reason why this is true is because the Kajan-Lustig polynomial is an Hilbert series. The thing we are missing is a combinatorial proof of this fact. So we don't know why this polynomial, which is supposed to be a combinatorial object, has non-negative coefficients. So a conjecture that is still open is proving combinatorially that this is true. So geometry already give us a confirmation. So we know that if we try to prove this conjecture, we will not spend decades to prove something wrong. We already know that this is true. How do we prove it combinatorially? So a way to give partial answers to this is using, oops, sorry, nope. should be faster to drive around. Okay. A way to prove it is to use this formula. So a thing that we were able to do in one of the papers, I don't remember. Oh no, sorry. I guess it's this one, the one with Luis and George. Sorry, I should know my results better than this, but one thing
It
we
feels
proved,
probably very good to not know.
one thing we proved is that for paving Matroid, this formula holds. And then doing some combinatorial inequalities, we were able to show that this difference was non-negative. And moreover, here I didn't explain everything, but basically we have a bound over how many lambda h times we need to subtract this thing. And since we know it, we know what the coefficients of these polynomials are, and we know what the coefficients of these polynomials are, and we know that we are subtracting not too many times these coefficients from these coefficients. So we end up with something positive because we were able to do a lot of weird, difficult, hard inequalities. But this again was just for sparse paving Matroids, so not for all Matroids. So if anyone has any idea on how to prove this combinatorially, please let me know. It's a nightmare that's been going on for years now.
Thank you. That was very helpful. Thank you.
All right, so maybe let's give Lorenzo another round of applause. Yeah, that was a really nice talk. And as
you
some people
very
have said in the chat, a great start to the semester.
Thank you. Appreciate
okay.
it.
So I guess we can stop the recording.